AP Chemistry, Unit 2.4, Structures of Metals and Alloys. So metallic bonds are going to involve positive metal ions surrounded by a quote-unquote sea of mobile electrons. Those are going to be delocalized electrons. No individual atom is going to own any particular electron. Instead, they are communally owned. No one has more of a share than anybody else. That causes some unique properties for our metals. So some properties for metals are going to be that we have a good conductor of electricity. They are going to be malleable. That means that they are bendable, and they are going to be ductile, which means that I can pull them out and extract them out into a wire. So again, for how this would be represented, we're going to have our individual atoms of our metal, and they are going to be positively charged, and then we are going to have a sea of electrons around them that are able to move freely and relocate at any point. Important thing to note for your metals and how they compare to your ionic compounds, specifically with electrical conduction, since metals have mobile valence electrons, they are able to conduct electricity. However, the ionic compounds, the electrons aren't the things that are moving to conduct electricity. Instead, ionic compounds, in order to be able to conduct electricity, the actual full anion or cation needs to move, and the metals are going to have those sea of electrons be the things that are moving. Alloys are going to be mixtures of metals, and you're going to have two or more, and they will have a unique list of properties because of there being multiple types of metals within that mixture. There are two types of alloys, two main types of alloys. The first one is going to be substitutional alloys, and those are going to be for atoms of comparable radii. So I can individually switch out those atoms, and they are going to substitute for one another within a lattice. So zinc and copper both have relatively similar atomic radii, and so they are going to be substitutional. And I can just replace this individual copper molecule with a zinc, and for my lattice, for my metal lattice, and that would allow me to make brass. This is going to be in comparison to interstitial alloys. So prefix in means like in between, and my interstitial alloys, those are going to be my atoms of different radii. And the smaller atoms are going to be able to fill in individual like spaces and gaps in between the larger atoms. And usually this changes the alloy's properties so that the alloy is stronger than the larger atomed base metal. And some examples of interstitial alloys would be steel. So carbon atoms are introduced to iron, and the carbon is able to go ahead and fill in gaps in between the iron atoms, since carbon is so much smaller than iron. And this would be an interstitial alloy because the carbon's not replacing the iron, but is instead kind of squeezing in between. So cupryl nickel is an alloy that's used to make coins made up of copper and nickel. Using atomic radii data below, which model is going to be most representative, and then we're going to judge our answer. So we can see that copper is going to have a atomic radius of 128 picometers, whereas my nickel is going to have an atomic radius of 163 picometers. And then I'm going to be looking at the differential between if this would be an interstitial alloy or if this would be a substitutional alloy. This is going to be a substitutional alloy, so B would be a better representation since copper and nickel are going to have like relatively similar radii, and thus a substitutional alloy would be appropriate since our atoms are relatively close in size. They would be able to replace each other rather than copper being fully able to get in between any spaces between the nickel atoms. And so if we were to look at an interstitial alloy made up of two elements, X and Y, where Y was the base metal, and the alloy was 20% of the new additional and 80% of the base metal Y, we would draw a diagram. So we would want to make sure that we had appropriate percentages, appropriate proportions here. And again, the Y would be our base metal. It's going to be our larger atomed thing. So for Y, we have these large circles here. We know that the alloy should be 80% of the Y, so we have a grand total of 8 of the Y atoms there. And then 20% of the X, so we just have 2 of the X atoms, and it being interstitial means that it's going to just fill in some gaps. So this would be an appropriate diagram for this question.